moving average. So this is a full form of ARIMA, or AutoRegressive Integrated Moving Average. So the if you look at here, we might have heard earlier about regression, but we might have also heard about the moving average. So here we are talking about the two different terms, autoregressive and moving average. They are different from what we have done earlier in terms of regression and in terms of moving average. So autoregressive integrated moving average means, suppose, what is the meaning of auto? The meaning of auto is that when we are trying to find we are trying to create the independent variable and dependent variable from the same variable. For example, if I have a sales of a product, right? If I have a sales of product, and let's say I have the time period of this product. Time period means like whatever the time period, maybe January, February, March, or maybe it's week 1, week 2, week 3, or it's day 1, day 2, day 3. So I will mention that in terms of numbers. I'm not going to mention them in terms of their actual name. So in terms of instead of writing January, Feb, or week 1, week 2, or day 1, day 2, or quarter 1, quarter, instead of mentioning them like that, I'm mentioning that as 125 here, and I have a sales of the product. For example, let me say I have a sales is 20 to 100 random. I'm taking a random number. I'm not using any kind of specific data over here. So this is my sales, and if I am talking about auto-regressive, the meaning of auto is that we are trying to create the independent variable from the dependent variable. So if I have to get the independent variable from the dependent variable, is that I'm going to take the lag of this sale. Lag of sales means, suppose I take lag 1, means my sale period 2 is influencing my period 1. What is the probability? What is the probability of my period 2 sale is in period 1 sale is influencing the period 2? What is the probability of period 2 sales in influencing the period 3? Means we have some kind of pattern where the pattern is that the past period is impacting the the exact consequent period sales, right? So for example, if I have to measure this, if I have to understand whether my past sale is impacting the very immediate consequent sale, right? Like 23, the period 1 sale is impacting the period 2 sale, or period 2 sale is impacting the period 3 sale, and period 3 sale is impacting the period 4 sale. So what is the probability of that, right? So I am going to build a independent variable from the dependent variable. My sales or product is a dependent variable. I am going to build the independent variable from the sales of the product. I am going to name that, say, lag 1 of sale, right? This is called lag 1 of sale. This is my independent variable. If I have to build a lag 2 of sale, lag 2 sale means what is the probability of my period 1 impacting the period 3 of the sales? What is the probability of my period 2 sales impacting the period 4 sales of the sales, right? In this case, we are not trying to find the impact of the two immediate consequent sales, but we are trying to find the impact of the past sales by giving a gap of one period, and finding the impact of that period to the next, by giving one period gap. So like this, a period 1 to period 3 correlation, period 2 to period 4 correlations. In this, if you look at, we have excluded period number 2 when we are trying to find the impact of, or the correlation of period 1 to period 3. We have excluded 2. Now we are trying to find the impact of the period 2 to period 4. We have excluded period number 3. So if I have to create this lag 2, so I'm going to insert this here. Now look at here, my period lag 2, we are trying to find the impact of 23 on, let me start from here, that's here. So this is going to start from here, not from there. So lag 2. Now if you look at here, the impact of 72 over 76, right? So we are trying to find the correlation between 72 and 76. We're trying to find the impact of 61 over 63. So the impact of 61 over 63. This particular, the data structure we're creating in such a way that the periods, the impacting periods are falling parallel to each other. So 76 to 72, 72 to 76, right? Then 61 to 63, 61 to 63. So like this, we are trying to create the independent variable from the same dependent variable, right? So I don't need to write this, I don't need to do this copy paste, or I don't need to do the linking with one. I can use a formula in Excel called offset. So I'm not going to explain the formula of offset here because we don't have so much time to explain it, to explain that. But if you want to create this kind of data structure, you can use a formula called offset. In offset, you have to take a reference point. For example, if I take a reference point here, right? For this reference point, how many rows I have to go? I have to go to one row. How many columns I have to go? I have to go 0 columns. For example, I don't need to go height and width. So I'm able to select the 88 from here, right? So 88, so I'm going to select. So like this, if I have to get nothing, 1 and put 0 here, I'm going to get some same data point here, 70, 70, 50, let's 41, 59, 68, 79, see, I can create a data set like this. Now if I want to drag this to next point, I get 0, but if I drag this to, so now if you look at here, I'm getting my lag 1 here, right? If I have to select this over here and I have to drag this point again, now I'm getting my lag 2 here, right? So I don't need to means create a linkage with copy and with linkage like this. I can simply use a formula offset. This offset formula can help me to create the data structure. So I'm not going to mention all. So what we are doing is that now we are trying to create our independent variables lag 1, lag 2, lag 3 from the same dependent variable. And the reason why we're creating these lags, because we believe that there is a correlation between the sales of the same independent variable, of various periods. So if you do this kind of study, and find a correlation, if I have to find a correlation for this, I'll go to data. I'll go to data, then I'll go to data analysis. I see data analysis here, and this I go to correlation, and I select my range from here. If I select the range over here, let me do one thing before that. I'll put all of them as 0 wherever I have a blank, right? So this will actually help me to create a uniform structure. If you want, there's another way to do this, but I'm going to take this method. So let me go and create my correlation here. So I'm going to select my sales of, I'm going to select my independent variable and dependent variables. I say I'm grouping by columns. My first row is the header. I have labels on this. I'm going to like my output range. Let me take my output range somewhere here and click OK. Now, if you look at here, I'm going to exclude this particular column from here. I'm going to click contents. Now this is what I'm going to also exclude my first row. Now if you look at here, my lag 1 to lag sales of product has a negative correlation, but it looks quite significant. That's minus 32, minus 0.32. So almost negative 32% correlation over here. So lag 1 has a correlation with my dependent variable. Lag 1 is my independent variable and sales of product is dependent variable. So lag 1 to my dependent variable sales has a negative correlation of 32%. Lag 2 has a negative correlation of 14%. Lag 3 has a negative correlation of 27%. So this is something, very significant, not very significant, but mildly significant, and is evidence, a good evidence to know that we have a significant number to suggest that we are seeing a correlation between periods of different sales. So when we find this metric, and this metric is called autocorrelation, right? And if you build a regression equation between these variables, this variable, then we call that as a autoregression. So if I use a linear function in Excel to build this is my y variable, this is my x variable, right? I need additional variables, so I put true and click close, and I'm getting my forecasting equation. And this is my auto regression forecast. So I'm going to build my forecast here. So what I'm going to do, I'm going to put my intercept here just to create the model, my coefficient of lag 1, my coefficient of lag number 2, my coefficient of lag number 3. So what you look at, what we see here, this is our, this is our r square, this is our r square value. So the r square value looks very poor. That is the 10%, 10.7%, 11%. So this is not a very significant model. So these are f test value 0.84, the 84% means there's 80. So there is the the variables which you have chosen, lag 1, lag 2, lag 3 are not a significant variable, because only 16% chance are there, they are 16, they are going to give a significant impact. 84% chance is that they are they don't have, they're not going to give a significant impact. That's the meaning of that. So only 60% probability is that they're going to have a significant impact. Means we're not going to generate a high accuracy. So the f test value, f not f test value, the probability of f test, the probability generated from f test. Now if you look at the 7%, so this looks very significant now. So r square 1%. Okay. So what I'm going to create is the forecast here. The forecast, now I'm going to take my intercept here. The intercept is f4 plus sum product, the sum product of my coefficients. I'm going to freeze them, comma. I'm going to take my the variables here and create the forecast over here. So if you look at here, I'm getting a forecast now. This is sales is 88 and the forecast is 74. The sales is 70. The forecast is 56. The sales 67. Then 68, 94, 61. So if you look at these numbers are not very encouraging, because our lags are not very. Our lags are not very significant variables, right? So if I want to create my mean absolute percentage error, so I'm going to take the absolute value of this, the forecast of all the values, minus the sales value, all the sales value, close the bracket, divide by the sales value, and I'm going to take the average of this entire range, and this will give the MAP of the data. And if you look at here, the MAP is 45%. This is very 46%, and this is very, very high. Means we are getting an accuracy of almost 54% only, right? So if I want to find this is my error rate, and if I want to find my accuracy of the forecast, this comes. Right now I'm using a random number, that's why it's changing again and again. So my accuracy is only 58.446%. And reason why we're getting such a low accuracy, because our R square value is only 15.4%. It's a very low R square value. Okay, so that's the reason why we are getting such a poor. And so lag 1, lag 2, lag 3 are not very significant variables, because our even if you have to find a t stat for each and every value. So let's say t stat for this is, I'm going to take my coefficient divided by the standard error. This is my standard error. So if you look at the t stat is 1.26, and if I have to find the p value for this, see, this is very, very high p value, right? This is 50%. We need these values less than 0.05. That's the standard value we are taking. So this is not less than 0.05. Everything is more, only the intercept is showing us less than 0.05, and rest everything is less than more than 0.05. If it is more than 0.05, it is clearly suggesting that our lag value is not a very significant value. Right? So the lag value, where t stat is coming, the t stat is 0.96, and the if you use sorry, t set is 0.038, and if you want to find the probability of this value exceeding the critical value, on how much, so the it's not exceeding critical value because it's coming around 96.595%. So this should be around less than 0.05. So this is not actually here. So what we're clearly suggesting is lag 1, 2, and 3 are not the significant lags determining the relationship, a strong relationship between the sales and lag with sales, right? I'll say with sales. So it's very clear. In this case, the lags are not very significant, so that's why we are getting a poor R square, this 0.05, and we're getting the error rate is almost equal to 45.9% is not acceptable. Accuracy is 54.1% is not acceptable. So this is how, what is, I just wanted to explain what is autocorrelation and what is auto regression. So we build autocorrelation over here, then we use these metrics to understand our, and then we build the auto regression. And in auto regression, the independent variables are lag 1, lag 2, lag 3, and dependent variable is a sale. And this is, if you look at, we use a function called linear estimation in Excel. This is our intercept. This is our coefficient of lag 1. This is a coefficient of lag 2. This is a coefficient of lag 3. Okay, this is our standard error. If you divide this coefficient by standard error, we get the t-stat value. Right, we get a t-stat value. So this is a t-stat value. And when we use t dot dist dot td by using degree of freedom as 24, because our sample size is 25. So sample size minus 1 is 24. So if you want to do this, so we get the t value, probability value 0.59. This should be less than 0.05. If it is less than 0.05, then we can say that we have 95% chance that there is strong relationship between the lag 1 and the sales product. If you look at here again, if you look at here, this 78, so this only 22% chance means we want this to be less than 0.05. If it's less than 0.05, we can say it has the probability of having a strong relationship between lag 2 and sales is more than 95%. Right now, it is only 22%. What is the probability right now having a relationship with the sales? It's only, so right now, some problems we are facing here. So, okay, I have to take the absolute value of this. If I take the absolute value, then I think we'll get the right. Will not face any kind of problems. Okay, now we're getting the right. So if you look at here, the 82% means like 17% is the probability, of having a relationship. You have to look at here. Now we are seeing here, some strong relationship, because our random variable, we are using a random variable. So that's why so there's 28% chance that there is a strong relationship between lag 1 and sales. The 22% chance there is a strong relationship between lag 2 and sales. There is 78% chance that there is a strong relationship with lag 1 and lag sales. So what we're saying is that, we're clearly saying that there is a very poor relationship between lag 1, lag 2, and lag 3. Of course, lag 1 is doing better than lag 2 and lag 3. So what we want is, what we want is that each variable should be, or maybe a couple of variables, showing the probability of having the relationship between with the sales at least more than 95%. So right now we're not getting none of them close to that range. Okay, so only the intercept is showing a great relevance. So if I try to avoid my coefficients 1 to 3 and just take only a basic naive forecast, I will do better in this case. Okay, so this is called the correlation, autocorrelation, autoregression. So how this is related? We already know that ARIMA. In ARIMA we have to take autoregression. So if you take autoregression, this plays a very important role. But in ARIMA, some of the important considerations we have to go and check is that the stationarity of the sales. What is stationarity of the sales? We'll check it. Then we have to also see that our error, which are or residuals which we are having, right? The residuals should not show any autocorrelation or patterns. We also have to see that error residual should have equal variance. We also have to make sure that error residuals have normal distribution. Right? These are the important considerations we have to go through to make to understand whether our ARIMA works very well. So there are various tests we have to perform for this. So to understand the stationarity of the sale, we'll perform augmented Dickey-Fuller test. To perform whether the errors have any autocorrelation or not, we will perform box-Pierce test, or another test called another L-Jung test. Either of one we can do. And to see whether our error have equal variance or not, we're going to perform the Bruce-Pagin test. Right. So these three tests, we have got normal distribution. We can do PV plotting. So I'm not going to go through the PV plotting right now. So I'm going to use only the augmented Dickey-Fuller test and box-Pierce test. Right. So let's try to understand the stationarity test on the same data which we have over here. So I'm going to take this data and paste it into a new sheet, and what I'm going to do here is that I'm going to frame my equation. Suppose my equation is that yt is equal to, okay, I have alpha plus beta into, I have suppose yt minus 1, that's a lag 1. Okay, so what I'm going to do now, I'm going to take a difference of yt minus 1 on both sides. This gives me equation now, alpha plus beta into yt minus 1 minus yt minus 1. So my left side becomes delta y is equal to alpha plus, I'm going to take yt minus 1 in common, so this becomes a beta minus 1 into yt minus 1. What is the usefulness of this equation? So if you look at delta y, right? So if I have to delta y, so if I have to measure my delta y, I'm going to create a separate variable for that, and for that I'm going to do my differentiation with 42 minus 72. So this differentiation I'm going to proceed throughout. This is my delta y, and this delta y is my dependent variable. Now I have to create yt minus y. So yt minus 1. So yt minus 1 is my independent variable. So if I have to create my yt minus 1 independent variable, that is based upon the sales, right? So this is my yt minus 1. Okay, so I'm going to create an equation here based upon this formula, and I'm going to build a I'm going to use a linear function. Now known y is delta y, because we have seen that is our dependent variable. My known x is yt minus 1, that also we have seen. So now we got an equation over here that is 64.214 and minus 1.4, right? So now this is my, we know this is my, let me put a little over here. So this is my intercept, and this is my the lag of t minus 1, y, lag of y, right? So what I'm going to do, I'm going to find my t stat from this. So T stat is the coefficient divided by standard error. This is my standard error. So I've got my standard error, that is minus 0.52. Now I'm going to find my Dickey Fuller ADF critical value at 0.05, right? Having drift or constant. So if I have to find this, I have to take the table. I will look at the table. So I'm going to look at the table now here. So augmented Dickey Fuller test table, right? So if I look at this table, so we are taking off at 0.05 and our sample size is 25. Our sample size in 25 equal just equal 25. We don't have if it is 50 we'll go 50, if it is 25 to 50 we'll take 50, right? So our sample size currently is 25 and our and we are saying that we have a constant and no trend, right? So we have three tables here: no constant, no trend, constant, no trend, and constant trend. So we are saying we don't have any trend, but we have a constant. So if you look at here 25 and 0.05, the critical value comes here is minus 2.986, right? Minus 2.986, that's the critical value. So this is coming around minus 2.986. Okay. So before that also I have to define my null hypothesis and alternative hypothesis. Okay. So for that I just refer one document here. So if so this is my null and alternative hypothesis. So the time series has a unit rate and is non-stationary, and the time series does not have a unit rate and is stationary. So let's see, if you look at this particular column, so if the T stat is less than, if the T stat is less than the critical value, ADF critical value, so we are going to reject null hypothesis, right? So let me also look at this. Yeah, the T status is less than the critical value, we're going to reject the null hypothesis. So in this case, if you look at here, the T stat is minus 5.21 and the critical value is minus 2.986. So here clearly the T stat is less than the predictor. So we are going to reject a null hypothesis here. So what is the null hypothesis? Reject null hypothesis. Time series are unit and non-stationary. So what we say, this data is stationary. Data which we have is stationary. So the ARIMA, the data which we need for ARIMA should have a stationary data. So what is the stationary data? So if you want to understand what is stationary data, so if you want, so at various intervals various intervals, the fixed intervals, if we choose around a sales period, we need to have equal mean, equal equal variance. Okay. So this is something what we have to look at: equal mean and equal variance. If we have equal mean and equal variance, right, we can call data as stationary. Okay, and all no patterns. No patterns means no trend and no seasonality. So if we have a data set, so if let us plot this sales data, let's see whether we have any kind of patterns here or not, or whether it looks like. If you look at this data, this looks like it have there is a common, this center line, that's a mean. It looks almost having, if you look, it has equal variance and equal mean, and it does not show any kind of patterns here. So this data looks stationary, and this is what the a Dickey Fuller test also is suggesting to us. The T stat is less than the ADF critical value. If T stat less than ADF critical value, we are going to have reject null hypothesis. Now let's say I'm going to create some pattern in this data. So we will see some other metrics now. I'm going to create a patterns over here. So I'm just trying to create intentionally some patterns. Let's look at the chart now. See the chart now, it looks almost having some kind of pattern here. So let's look at the data. See, this data now looks having a pattern. So this is having a trend pattern. If it's having a trend pattern, it means we have already mentioned the definition of stationarity. If it's not having equal mean, equal variance, and it displays trend and seasonality pattern, so data is not stationary. So now if you look at the data, is clearly showing a trend pattern because the initial point is low and the ending point is high. So this shows that there is a trend over here. Now let's look at our test values. Now if you look at in this case, the t stat is 2.65. We don't need to create the equation once again because the data is automatically going to create the regression equation because we already have given the formula. So it is dynamic. If your data changes, also not a problem because we're going to get a dynamic results over here. So now the t stat is 2.65 and ADF critical value is minus 2.96. So in this case, the t stat is more than, in this case, the t stat is more than the ADF critical value. If t stat is more than critical value, then we're going to accept a null hypothesis, right? If you're going to accept a null hypothesis, it means it is going to be data is non-stationary. So it's clearly suggesting the t stat is more than. Now in the second case, the t stat is more than the ADF critical value. If this is a case, then we have no strong reason to reject the null hypothesis. So we are not going to reject the null hypothesis because we don't have any, hence data is non-stationary, right? The data is not stationary. So this, if we have this kind of patterns in the data, means we have trend or seasonality, or we do not have equal variance, equal mean, it means that data is not suitable for ARIMA. So what we say, the data is not stationary. We may not use that data directly for ARIMA. So in that case, what we're going to do, we're going to create a stationary, we are going to create a stationarity here. To create the stationary data, what we're going to do, we are going to do differencing. So we have done the differentiation already over here. So if you do the differencing, so some kind of linearity might come. So let's plot this graph and see whether we're getting a linearity, anything linearity inside here. So I'm going to build a scene within this only. So I'm going to say my differencing data. So differencing data, how it is being plotted. So this is my difference data. Create the for, let's see how the difference data looks like. Now if you look at the difference data, which is red, like this looks quite stationary, right? This not show as much trend as the first one. This looks quite better. This is one of the technique of creating a stationary part. Let's say we go to a second technique that's called log. So I'm going to take log to the base 10, and let's see if this shows another way of creating the non-stationary data. So there are many techniques out there. So I'm going to show not all the techniques to you right now. I'm going to work on a couple of techniques only to explain what is the difference between stationary and look. This looks complete linear. That is a complete linear transformation. I don't want to bring a linear transformation here. I just want to keep it, the difference part, and we're going to take the difference part, differencing data to, take the ARIMA into account and build a model. So, I'm going to copy this data again and paste here. I'm going to create the difference because we need to create difference to create a stationary data, which is our new dependent variable. So these are dependent variable, right? For example, if we so now we have difference data, right? Now what I'm going to do is this difference data is my dependent variable. Why? Because this shows some kind of stationarity in the some kind of stationarity in the data, right? Before that, I also want to like to build my autocorrelation. So I'm going to write a formula. If offset is equal to 0, give me blank, or else give me the offset, right? So this is the formula which I'm using here. So this gives me immediate, I don't have to, it takes very less time to create the output. Now I'm going to create my correlation and build my PSA, means I'm going to build my, go to correlation here. So I'm going to take this data set and I'm going to name this, okay, there is a problem here. I'm going to change my range once again. I'm going to change my range and also I'm going to create, no, I'm going to select this entire data from here. Okay. And I'm going to name them, I'm going to bring my nominations or heading nominations over here. This will be much better because we want to see our nominations headers or the, now I'm going to go and create the input range. The input range is here, is this one. Okay, I'm going to take my output range. So output range I can take anywhere here, not a issue. So now if I, this is my output I'm getting here. So I'm going to build my bar chart. So if you look at this bar chart, it's clearly suggesting there is a strong correlation. So this is my autocorrelation chart. So this autocorrelation chart strongly suggests to me that there is a strong pattern available in the in the sales. Now, for example, if I go with differencing data, I'm going to build my, so what I'm going to do now is instead of building this, say, instead of building the lag 1, lag 2, lag 3, lag 4 based upon my sales, I'm going to build the same thing on the base of my differencing data. So I'm into D2. Instead of D2, I'm going to use C2 here. So C3, right? I'm going to use C3 here. I'm going to use C3 here. Just I'm changing the reference because I want to create my differencing data lag. So once again, I'm going to drag this down and drag this down. So what I have done here is, let us see, this is D3 is taking C3. Okay, this is C3, C3, and I have to carry the C3 all across. So if I have to carry C3 all across, then I have to freeze this C3. C, I have to freeze this C, right? I have to freeze the C. Okay, let's try it now because we have to get the right output. Okay, now we got C here. Hmm, hmm. Now we have to go to E. Sorry, this was fine. Everything was fine earlier. There's no problem with C. So we have to start from here, the E, because the sequence is changing. Now it's going to work. So we got our, the data over here. So now what I'm going to do is that I'm going to build the autocorrelation based upon our lags. For that, I'm going to remove this much part. I'm going to remove this also. Now I'm going to build my autocorrelation data correlation. My new range is our difference data columns. I'm going to output range. I need the output somewhere here. Click on OK. So now I'm going to build so let us look at this once again. So I will just want to look at my range correlation. So input range is B73 to N85, right? So B73, okay, B73 to N85. There's no, that makes sense here. So 1 minus 20 minus 20 minus 30 minus 135 minus 100 minus 35. Okay. So what we see again, we see a strong correlation. Means let me show you. So we still see a very strong correlation. It means our data is not still stationary, but it is not as strong as the previous one. But it is still showing. It's very strangely it is showing a strong correlation here. So what we have to do is that now, so this is not a very, let us see if this is right. 100 minus, the difference is B3 minus, okay, okay, not a problem here. So this is 100 minus 72. Okay, now it looks good. Okay, so now I'm going to paste from here. So we'll manage this there. So now if I take this and paste here and take the differencing values from here and paste them here, and we'll build this model once again. Okay, so I'll go back to data. I took some copy paste issues there. Okay, so there are some issues. Let's correct them, because wherever we have blanks, it has to replace. We'll replace it with 0. Control F. Replace this with 0. Replace all. Close. Now we're going to do this calculation again. So now we'll build this correlation chart, autocorrelation chart. Now if you look at here, we see a clear case of the we have managed to make data stationary, because the autocorrelation chart for this sales data without differencing and autocorrelation chart of sales data with differencing, there's a difference. So there is a we are seeing a clear case where at lag 1 we are seeing a at after lag 1 we're seeing, or after lag 2 we are seeing a death of the correlations. So there is no significant correlation after lag 1 or lag 2. But in this case of the normal sales data, we see a significant correlation till lag number 12. So there is a serial autocorrelation present in the sales data. But when we look at the difference data, the correlation is either dying at 1 or at 2. It depends upon the analyst, or it depends upon the model. Shall we say that the correlation is dying at 1 or 2? It depends upon the analyst, or we can go with the simulation of both the lags. So this is how we are seeing that saying okay. So this is how we are seeing that there is the differencing is creating a stationarity in data and killing a trend pattern. Okay. Now we have to create the model. We have to create the model with the differencing what we have done here. But with that, we have to create our model. So for example, I see how many lags are significant here, right? We are the difference data, we see a significant lag of 1 lag is, so, or 2 lags. So this particular autocorrelation chart is used to decide the order of MA. This is used to decide the order of MA. So how many uh, how many lags of error we should actually take into the model. For example, if I have to build the ARIMA model, so my ARIMA model is right. So we are saying that delta y is equal to, delta y is what? We are saying yt minus 1, yt minus yt minus 1, right? So y2 minus y2 minus 1, or y3 minus y3 minus 2. This is equal to alpha plus beta into, right, lag 1 of differencing plus lag 2 of differencing, like this, plus error at t plus error lag 1 of error plus lag 2 of error right? This is a formula which we use to create the ARIMA function, right? So here we have to decide how many lakhs of differencing we have to take and how many lakhs of error we have to take. So how many lakhs of error? How many lakhs of error is decided by autocorrelation chart, and how many lakhs of differencing is decided by partial autocorrelation chart. So we have just done our autocorrelation. Now we are going to do our partial autocorrelation. So in partial autocorrelation, we'll understand how many lakhs of you know. So for that, what I'm going to take, I'm going to take this sales of product, sales, get the lakhs. So now, if you look at here, I'm taking there's two possibilities over here. So this data which we have initially, it is a non-stationary data. Right now, after we have made this data stationary by taking the differencing. So I'm going to first build. I'm going to first some of the product, some of sales of the product, right? So I'm going to sales of the product 28. I'm going to remove this from here. Okay. So what I'm going to do now, I'm going to build the linear regression equation. So first I'm going to take linearist, take my y. What is my y here? My y is differencing. What is my x here? Lag 1. Close the equation. So if you look at here, I'm getting my coefficient is okay. I have to find right. So if you look at here 1.85 and r square is 0.58 and 1.85 and 0.49 is my value here and 0.58 is okay. So 1.85 is the coefficient. Now I'm going to write this 1.85 and I'm going to measure my t stat here, that is 1.85 divided by 0.49. Okay, I'm going to take my r square, that is 0.58. Okay, Now what I'm going to do, I'm going to improve. So now what I'm going to do, I'm going to take the two legs now. So initially we took up to D. I'm going to make this as now C15 to C15 to C, and I'm going to do 15 to D. I'm going to take D to E. So I'm going to take lag 1 and lag 2 together, and I'm going to find the coefficient here. So the coefficient now here in this case is 0.03, and my T stat is 0.03 divided by 0.848, and my R square again is same, that is 0.58. Now I'm going to take three variables here, D, E and F, means I'm going to take lag 1, lag 2 and lag 3. D15 to F26, so D15 to F26. Okay, there's a problem here because now we have seeing a 0. We have to put wherever we have the open values, we have to put 0 there, because the model requires to have no empty columns. So I'm going to manually put zeros here. Now if you look at here, I'm getting so before that I have to go back to my previous equation. I'm going to make E F26. So here I'm getting my lag 2 is around 0.03. Okay, that's fine. Now I'm going to go to F26. I'm going to see the coefficient of lag 3, that is minus 0.32, minus 0.32, minus 0.32. Similarly, I'm going to go for now the 4 lags. So G26. Now it look at 0.41. I'm going to go and build the H26. I'm going to use more lags now. We're getting around minus 0.19. Right? So what I'm going to do now, I'm going to build a table out of this and build a chart of these coefficients. And this chart will be called as my partial autocorrelation chart. So partial autocorrelation chart, if you look at here, we're seeing a depth at number 2. So we are seeing clearly, the first lag is significant. So the partial autocorrelation chart suggests us the AR order is 1. The autocorrelation chart suggests us The MA could be 1 or 2. We'll try with both the models. And we have done differencing of the order is equal to 1. We have done single differencing. So AR is equal to 1. Different integration I integration is equal to 1 and MA is equal to 1. This could be one model. The other possibility is AR is equal to 2. Sorry, AR is equal to 1. Integration is 1 and MA could be 2. So we are going to build two models based upon this, and then we are going to test our model and the error, and then finally test the error rate. So I'm going to build this model now. I calculate my error. I'm going to calculate my lag 1 error, and because we have only single lag, so we have MA2 also, right? We have MA2 also. So I'm going to take 2 lags of error. So finally, I'm going to build a model. The model is YT by YT minus 1, right? That's a model. So we're going to pull our YT minus Y also inside it. So what is this YT minus 1? 135. So I'm going to use 135. So we are at this point. So I'm going to take 135 plus. Okay, first I have to build a model now. So I'm going to take this data from here, right? Go and paste into a new sheet. So whatever is not required, I'm going to delete that. These are final data set. Okay, I have to put one more array. So I'm going to put up to this point here. Okay, so I'm going to start modeling from here. So I'm going to take the first value 135 because this we are initially we take delta. So we are not forecasting not for delta. We have okay. Now we have to build our linearist equation first. So equal to linearist. So known wise is our differencing. Sorry, our sales. Let's say differencing. Then our known x is so we're going to take 1 lag from here. Sorry, we have to remove some data points from here. So lag 2 to lag number 12. I'm going to delete that. Right, I'm going to take this error and put here because we need to have continuation and when we build a model. Linearist, take the differencing as y, take lag 1, lag 2, lag. Okay, so this is what we're going to take. first the first model AR1, MA1. So this is the first equation. So let's say I'm going to fill first model forecast 1 with the AR1 integration 1 and MA1. So what I'm going to do first is I'm going to start building a model from here. I'm going to take 135 plus. So this is my intercept. Freeze it plus 2.24. Freeze it into the lag 1 of error plus next intercept. So let me freeze this genetic coefficient and then take this one, and I'm going to take my ET. ET is coming from here. Let us check the error here. The average minus A15, right? Okay. Instead of taking the average of entire data set, let's take the average up to 2 points. So this gives me average up to 2 points. Yeah, this looks better. So we are taking error lag 1, lag 2. This is 2.5, this is 2.5, and this is 5. This is 5, this is 5. Right? So this is 5, this is 5. So let me copy this and paste over here. There is some issue because we don't have to get so many data points here. 135 onwards, right? 135 onwards, we're getting here. So 135 onwards. So let me paste from here once again. Where is our yeah? So this is 135 onwards. Okay. So lag 1 error, lag 2 error. Let me paste it. Let me paste it here. Okay, now we are going to paste our error lags. Okay, now the forecast looks quite good. So the 145 is the sales, 149 is the forecast, 150 is the sales, 166 is the forecast, 200 is the sales, 184 is the forecast, 226 is the sales, 200 312 is the forecast. Right? This looks quite good now. So let's find the map of this. This is my forecast minus this is my sales divided by the sales and close the bracket. We're getting around 12.2, 12% as the error. If it is ARIMA, AR1, MA1 and division 1, right? Now let's try the same model with ARIMA 1 MA2, right? So we'll try with the MA2 model. So what I'm going to do, I'm going to change my model. So I'm going to take Linux again. So known wise is my differencing, lag 1, lag 1, lag 2. This time I'm taking all of them, right? So I'm going to build a model now. So 135 plus, take the intercept, freeze it, plus take the first coefficient, freeze it into the lag 1, no, lag 2, lag 1, sorry, lag 1, plus take the second coefficient, freeze it, and then take the second variable, plus take the third variable coefficient, freeze it, and take the lag 2, right? So what are you getting, exact, there is no difference between the forecast and the error. The forecast and the sales, we're getting exact values over here. The reason we're getting this because, the first variable intercept is almost equal to 0. The second lag 1 coefficient is almost equal to 0. The lag 2 of error is almost close to equal to 0. Only we are seeing the lag 1 of error. So this is showing like a MA model, MA1 model. It's purely MA1 model. That's why we're getting like this, right? So this is overfit. So we'll not go with this AR1 MA2 model. So this is an overfit model. We're getting complete. There is no difference between the forecast and the sales. So this is completely overfit model. So what you're going to take is AR1, I equal to 1, MA equal to 1 with 12% error. That's how we are going to go with this. So there are some additional checks we have to go do, but I'll not do this in this podcast. So there's we have to do error pattern, presence of correlation, or presence of serious autocorrelation in error, right? So that is we call as Lingjun test or box peer test. I'm not going to perform this. You can also get it from there. And equal variance test, equal variance in errors. That is called Bruce Pagan test. So I'm not going to perform here in this. So I wanted to show you the process of how to actually build a model in ARIMA. So first you have to check your autocorrelation, then you have to check your partial autocorrelation of your initial data to understand whether these patterns are present in, or you can directly go and perform the ADF, augmented Dickey-Fuller test, on the sales data. If you see any kind of patterns available in the as per, if the ADF test suggests that the data is not stationary, then you have to do single differencing. After do single differencing, again you have to perform the ADF test on the single differencing data and check whether you see any patterns over there. Like this, you can continue the test, and you have to understand when you're getting the ADF, or you can go and do the autocorrelation and partial autocorrelation to understand that. But I will suggest not to go with autocorrelation, partial autocorrelation to check the stationarity. You use autocorrelation, partial autocorrelation to understand what kind of order of AR and what kind of order of MA you have to choose, because that is going to help you to pick your model. Once you pick the model, create the forecast and do multiple simulation, and make a decision based upon your bias and variance. So in this case, the AR1 and I equal to 1, M equal to 2 shows overfit model, and I will not choose this. I'm going to go with AR1, I equal to 1, M equal to 1. So guys, we are launching a training program from 16th of August. 16th of August, and this is our weekend batches. Weekend batches. So if you want to learn machine learning based forecasting techniques, where you will learn like neural networks, XGBoost, like statistical models, and all kind of tests which you have to perform on data to understand whether data is suitable for forecasting or not. We also learn how to data clean the data, transform the data using SQL and Power Query, right? How to build a data visualization using Power BI. So if you want to learn the course based upon Python, Excel, SQL, Power BI, then I think you should join this course and advance your career, because right now the skills which you have in supply chain, that is not considered enough to proceed your career further. A lot of layoffs are going to happen. If you want to secure your future, then I think you have to learn the skills like Python, Power BI, SQL, and not only learn the skills, but how you can create the projects and create the improvements and transformation in your company. That is the most important thing. So if you want to contact me, you can contact me on my email ID, that is krishnaidu@mathnal.tech, or you can mail, or you can WhatsApp me at +91 7989 366 381, right? So please feel get in touch with me, and I'll be able to support you in building a good concepts or good skills on forecasting, which is something unique in your portfolio and among your peers, right? So look forward to you in coming sessions, and we'll be sharing more information about on the machine learning application through Python and Excel. Right now, we have given you one explanation on the Excel, but if you need to have all these steps in your mind, all these algorithms, all the steps in the algorithm in your mind, so that you can write the code in Python or use the packages in Python and do the correct interpretation, so that you can use the interpretation